nice introduction. Welcome, everyone. Thank you to the organization and committee for inviting me here. It's a great pleasure to reinforce our collaboration with INEGI over the last years, where we have been having different projects and also co-workers coming from INEGI, working at Fraunhofer. I'm happy to give you here today a general overview about applications we have been developing at Fraunhofer for space and aerospace in the field of additive manufacturing. So you're going to see here, obviously, material-related properties, but mostly the path, the way that led us to introduce these applications into industrial parts. At this point, I would like to also thank all the involved colleagues and doctorants and postdocs, students working with us. They led these experimental projects and work, and need to be definitely named here. So for those of you that are not maybe familiar with Fraunhofer, Fraunhofer is the biggest applied research association within Europe. It is distributed originally in the whole country of Germany. We have more than 76 institutes right now. In the last decades, we expanded also overseas to United States and Japan, definitely due to the importance of the industrial-related companies. And the interesting thing about Fraunhofer that is being also introduced to other European research institutes is that we are forced, let's say, to get 1/3 of our revenues directly from inquiries or from projects coming from industry. So we are not based on fundamental research, but we are always being evaluated by getting this money and needs from industry in our projects. The other 2/3 of the money usually arrive from public funded projects. Also 1/3 of them need to be directly with companies, and the other 1/3 is industrially related money gained by Fraunhofer, addressing more visionary projects, let's say in a scope of 10 years and plus of what is important concerning topics. Coming to our institute in Dresden, we are, as our name says, laser and material institute. So 1/2 of our divisions work in all related laser technologies, from cutting, joining, coating, up to additive manufacturing, and the other divisions are more related to coatings for the quite strong microelectronic industry in the area, and also photovoltaics. So these are the numbers, maybe not so exciting, but just the interesting point is we addressed in the last years, even if COVID was a major topic, they require 1/3 industrial revenues, and therefore we qualified, let's say, to get also some internal funding. Concerning the department of additive manufacturing, which I'm leading, we are divided in 3 groups. So we come originally with more than 25 years experience from the field of direct energy deposition. There's a metal deposition where we develop materials, system technology, and processes. So one group is dedicated there to that issue also, and combining these technologies with other conventional manufacturing. Then we have the powder bed process group and 2D printing, where we address laser, powder bed fusion, electron beam melting, binder jetting, and so on. And then finally, a 3rd smaller group addressing topics concerning simulation, for the other groups, process chain optimization, and all products that Fraunhofer develops, giving them, let's say, an homogeneous design and also industrialization. Once we have a product, we need to leave it there and it goes directly to industry. So we are around 35 technicians and engineers in the division, and more than 60 students that do also fundamental experimental work. So concerning the outline of this presentation, I'm gonna give you 3 major examples of applications in the field of space and aerospace: an optical bench, large part, an aerospike rocket engine, a middle-sized part, and then finally, completely different thing, a bionic ripper, a smaller part made out of polymers. You get this overview of different materials and different applications we work with. And finally, I have a small also outline of multi-material approaches, as we saw before in other presentations today, that might be relevant for us in the future. It might not be tightly understood, let's say, why additive manufacturing is interesting for large parts. I'm talking about 1 meter and more. But if you take a further look at the motivation or at the advantages that we can introduce by adding additive manufacturing to these big parts manufacturing, you would see that we can address the buy-to-fly ratio and optimize it for these large parts, reduce lead times, also combine technologies to do repairing, which is also in the scope of sustainability, and enable by adding filigree structures new design approaches. So far, we have been addressing in major projects these materials you can see here: titanium, steel, superalloys, mostly nickel base, but also high entropy alloys and so on. And aluminum, as aluminum is also quite interesting for the space and industry due to its good stiffness properties and lightweight design possibilities. So the example I brought you today is a major European Space Agency project called the Athena mission. In that project, we have been developing for the last 5 years an optical bench addressed to this Athena mission, which aims to an advanced telescope for high energy astrophysics. So the intention of ESA is to explore hot and energetic universe with advanced X-ray technologies. We are aiming to develop an optical bench, you will see it later on, to give hold to different mirrors, optical mirrors. And this Athena mission is integrated in the laser interferometer antenna called LISA project, and will be placed in the L2 orbit out there. The mission is scheduled for the year 2034. So we have manufactured a first optical bench and scaling up to a higher one. And the first one is being tested for the application and also being compared to other competitive technologies for the setting up into space. Concerning material properties that we need to give to this optical bench, you see it here, represented here before manufacturing. We need high specific stiffness, an overall coefficient of thermal expansion, also an aligned coefficient of thermal expansion concerning the bench and the modules with the optical mirrors. And therefore, after some considerations, we came out to the idea of fabricating this optical bench after the titanium 6-4. Other parts will address this optical bench in aluminum by combining normal manufacturing or conventional manufacturing and milling. But concerning the oxidation issues and also reflection issues, we didn't follow the path with aluminum, but address titanium as the alternative in our case. Obviously, titanium leads to other issues like milling, which is also quite challenging. The oxidation issues, so we studied, let's say, the introduction of flatted atmosphere or local shielding to the process. And then you will see later on what are our choices for the fabrication of the optical bench. So we came across to the idea of working on a double robot system for milling and manufacturing. The milling robot can also be substituted by a laser metal deposition machine to increase productivity for some areas of the optical bench. The absolute accuracy is 180 micrometers and repeatability is 70. And then we introduced a huge amount of process monitoring developed by Fraunhofer IWS, like melt pool analysis, EMAX, and other LISEC process monitoring devices, studying the nozzle condition. So if we have approaches like collision or the nozzles are working properly. A huge issue as we are working in an open atmosphere is obviously the laser safety and also particle safety. So we develop also the so-called powder screen measurement system to measure particle in suspensions in the lab to assure that the co-workers were not affected by these things. So a couple of things you need to take into consideration. It's a huge headache, obviously, to print such a huge part. We are talking about 1.5 meter for the first prototype. So all of these things need to be important, taken into consideration. And then obviously We need high productivity ranges over kilograms per hour, sufficient material. We studied the scope of working with wire and powder. Due to the geometrical complexity, we moved to powder approaches because the wire was not able to give us the exact geometry steps needed there. And obviously distortion and residual stresses are a huge issue. If we work also for a couple of days and hours printing layer after layer for a 1.5 meter structure, you might have included residual stresses that lead to the lamination, and even huge forces are related into the printing. So you have to address also security in the lab and not having an issue with that. So one of the nice residual effects of printing such a part was the development of a new nozzle to our family, coax nozzle, with integrated gas shielding device. You see this is a quite wide nozzle, where to avoid the whole flooding of the lab, we decided to create a laminar flow area direct to the substrate to get by these melt pool sizes and velocities you can see over there, a well isolated area to avoid the isolation of, also to avoid the oxidation, sorry, of titanium parts. In the video, I can make it run for you. You can see the printing during the process with the two robots. As mentioned, where at some points we substituted the one of the process here by 1 million unit to get the exact areas for the optical mirrors there. But usually to increase productivity, we were working with this two robot approach for the printing. Concerning design, we have a couple of issues working quite close with ESA, because as you can imagine, some of the previous design approaches were not so AM friendly. So therefore, we needed to take at critical parts like the spoke, inner rims, outer rims, and pockets, closely approaches. For instance, we don't have the possibility working with DD of having support structures. Therefore, we changed the geometry of these spokes and pinholes to avoid the need of support structures and made them more DED friendly structure. You can see it here. So we also need to take into consideration that we have a similar moment of inertia and mass in all of the related areas for the printing. And we also wanted was to have reduce post-treatment requirement, so that we don't need to, let's say, modify the whole structure in not accessible areas in the optical bench. So some of the things to take into consideration. Working with this 1.5 meter parts, we started, we didn't want oxidation, we wanted proper tensile properties and also no distortion. We started with a quite conservative laser power of 2.5 kilowatts and 2 in the very beginning days. And then as we are aiming now to 3 meter diameter part, which is going to be the part shipped to the outside or to the space, we moved to a 10 kilowatt process. So you can imagine you cannot directly move all parameters or translate all of the related knowledge to the steam 10 kilowatts. And therefore we started identifying areas where this processing incrementation was not that critical, and combining both strategies to reduce here in the diagram the building job duration. The idea is once we start with the printed, we started already of the 3 meter structure to move continuously to part by part or area by area to this 10 kilowatt approach, let's say. So that's for these 3 meters, these are the expected values of the geometry and also of the gas flow and so on. You see here some of the related first experiments where we also we'll be working with flipping, as moving the table 180 degrees to avoid distortion. You see here on the substrate that this might be an issue, but compensating through flipping of the table, we expect that the 3-meter optical bench will be printed up without let's say, significant distortion. The structural integrity is obviously an issue, so therefore we had test campaigns related to the optical bench. We cannot print the whole part and then test it, but we have been aiming to a representative geometry that we can print easily and then test all of these properties you can see here. So grain size and orientation, tensile testing, and fracture toughness testing and fatigue. And we came out to the idea of having thinner and thicker walls to study, let's say, the effect of the heat flow. So it is expected that we have a different microstructure strongly influenced by thermal gradients, and therefore we started with thinner and thicker demonstrators. And then interestingly, what we have seen here is the microstructure and the thin geometries, and in the thicker areas show no significant visual differences. As I have to say, also we have integrated intermediate heat treatments during the process. So this seems to compensate, let's say, some of the issues of the expected thermal gradients. And we had very significant or very similar, results from mechanical properties. So in terms of saving time and resources, we moved to the thinner wall approach to, let's say, follow up all of these fatigue and mechanical properties. So summarizing at this step for this application, we are fabricating the final demonstrator from 1.5 meters to approximately 3 meters. We started right now in the late summer. And in the meantime, the original prototype is being tested by ESA and being submitted to conditions that are similar to the ones expected in the Athena mission. The second example, more related to the middle term part concerning the size, is the hydrogen peroxide kerosene aerospike breadboard engine. Aerospike rocket engines have been actually developed, the idea, in the 60s, but there was not real useful technology to fabricate them. So we had the issue that they have very complex inner structures and geometries, and there was no significant technology that can address these things. Concerning or compared to a bell nozzle, we have which are the conventional rocket engines, we have the detrimental effect in a bell nozzle engine that there is an influence of the different altitudes with setting these satellites thrusted by the aerospike rocket engines into space. And while using an aerospike thruster, we are quite independent for the total efficiency of the altitude. So we are more efficiently working also in terms of saving fuel and in terms of the total energy balance. We have also, I don't know if you can see it here, but in the next slide, cooling channels and also fuel redirecting channels inside that lead to preheating also of the fuel, so we can be more energetical efficient than conventional, let's say, rocket engines. And it is also expected to have a lightweight design, saving around 30% of the mass of conventional engines by using this approach. In this case, we're not experts actually in the design of such rocket engines, so we started a collaboration funded by ESA with the Technical University in Dresden, the design department for such applications. And this is the, let's say, natural development of our designs. Also, the size is quite different. We started here with a quite small first demonstrator, 100 millimeters, and now around 500 millimeters height right now for the actual demonstrator. We changed also the post treatment of the cooling channels and heating channels to increase efficiency and also to modify the dynamic flow. And we are moving also to different materials. We started with titanium and moved to Inconel due to high temperature properties, and also are addressing copper right now, EG62, also alloy to get also a good advantage of the good thermal properties of copper. So these are some of the developments concerning the structural integrity. This is the common process chain for you to see without getting into the details due to the time, but this is the common thing that we are doing. For the bigger aerospike rocket engines, we are combining conventional manufacturing, so welding and AM due to the issues with the size. So we are, in some cases, printing two separately parts, the rod and the tip, and then welding them. And also to increase the high temperature properties, we realize there is some kind of limitation with Inconel, even if we submitted to heat treatment concerning higher temperatures, and therefore we introduce also in some thermal critical areas a TVC coating, thermal barrier coating, sorry, to increase this resistance against thermal issues. Concerning surface roughness, which is relevant also for a good flow of the fuel and the cooling liquids, we studied different layer thicknesses of this LPBF process, 30, 60, and 90, and get along with the result that 30 micrometers layer thickness give us an average 40 lower roughness than other approaches. And that's exactly what we want also to get a good hydrodynamic structure in the aerospike nozzle. Concerning mechanical characterization, also in some of tests that we have been addressing for this 30 to 60 micrometers, we took the 30 micrometer layer thickness optimized already concerning roughness, and the values were superior in all mechanical aspects to the expected parts, also exceeding the AM requirements for this kind of application for the UTS and also yield strength at room temperature. So we were quite confidential also that the results could be nice for the real testing. And then you see here what I mentioned, the welding of the rod to the spike interface to scale up to higher force values, this aerospike, and the introduction of the TVC for increasing also the performance in the level of higher temperatures. Another issue for us is by using simulation, in the third group I introduced to you, avoiding issues related to filigrane structures before manufacturing, and if we are lucky, also to spare some of the steps in the process chain. So we introduce thermomechanical and also thermal simulation to see where we have critical thermal affected areas. We came out with this is the highest temperature, but these filigrane structures are very dangerously affected by distortion and also lack of fusion and so on. And this process simulation helped to better control the deformation and stresses, so we could save time and also adaptive support structures were needed to avoid these deformations in the past. So it's a step that I would also recommend to you if you are working with such parts or applications. So coming to the final use, together with our partners, we tested the aerospikes in the conditions required for the functional approach. And you see here the fuels used and so on. This is experimental setup at the Technical University in Dresden. And we saw let's say, less beneficial properties if we work without the post-processing, without the smoothing of the inner channels. But once we go to AFM approaches of smoothing and post-processing the inner channels, we can get even better performance than the bell nozzles used in industry for these micro launchers and satellite business, which is going to increase in the next years around a factor of 5, as the ESA also is expecting. So finally, and quite quickly, the third application, it's a completely different application in the field of polymer, but also interesting due to this bionic and topology optimized approach. We develop different grippers in the past, maybe not so exciting, out of metal, for instance, for the microelectronic industry in Dresden for the use for transportation of wafers and so on. But the interesting thing is that in nature, there is the so-called fin ray effect, where if you work with this fin ray fish, you see that when submitted or affected by a force in this fin area, the fin area does not bend over, but they adjust to the geometry of the object being applying this force. So this can be used to manufacture grippers for different applications. For instance, for the food industry, to transport quite delicate products, also for maritime probe or sample again in the area. But the interesting thing for us is the use in space, also for the transport of different delicate substances or samples, and also for the transportation of, let's say, also parts that are applying some kind of force against the gripper and need to be transported under non-gravity or different gravity conditions. So what we did, we printed these fin ray grippers by FFF, and then introduced what we wanted to monitor were the different forces applied there in the gripper. So we added the further printing technology, so dispensing, to print a wide range of different sensors. As you can imagine, you can measure deformation, the position where exactly your object is being placed, concerning the gripper, temperature, distance, whatever. And you see here the expected area where we can place these sensors. That was the theory, and this is the practical aspects by working with silver paste and FFF, and also dispensing technologies. And you see already some integrated sensors, pressure, deformation, and so on. And actually you can work with a polymer, which is a thermoplastic polyurethane, with no issues concerning the drying by 110 degrees. And obviously it's not so easy as I'm telling. There are some issues obviously concerning contacting or printing on the ribbon cables. You need to take all of these things into consideration. But we have already developed a prototype with the company Evologics being involved in this project for space applications for future things. And last but not least, as I mentioned, we saw today also in the previous plenary talk, some interesting applications in the field of multi-material. We do think this is also one of the things we're going to see, big things in the next future for space and aerospace application, the combination of materials, for instance, also here, superalloys and ceramic for high temperature application in turbines, or maybe graded structure, graded transitions of different metals to address challenges in just localized areas of our parts without commenting on all of this. This is it. Thank you for your attention. I hope I could lead you to a brief overview of some of our activities. And if there are any questions from your side, I'm happy to answer them.
Thank you, Elena. Okay, so the floor is open for the discussion. We very quick. Any questions? Any further? Yeah, please.
Thank you for the presentation. A question about the setup of for the production of the optical bench. You mentioned like a very good accuracy, and that's difficult to obtain with robotic arms plus a rotary table plus that kind of process. So how do you obtain such a good accuracy?
This accuracy is obviously being given by the robot arm. As you mentioned, we have also some freedom of movement in the tables, 2 degrees of freedom, 7 and 7 for each robot. So we made a screening, let's say, of the possibilities we had with CNC units or with gantry systems or robots, and then came up with this system for ABB, where we had these values of repeatability and accuracy. So it's given by the robot system itself.
Thank you.